Excellent. You have arrived at lesson 3 in our solutions unit. In this unit lesson, we're going to cover solutions and solubility guidelines. Okay, and our learning target is to be able to understand. I can identify the solvent within a homogeneous solution, and 2, use table F to predict solubility of ionic compounds in water. Okay. Oh, there's a third one. And use our term like dissolves like to determine if two substances will mix. Okay, so here we go. Solutions are homogeneous mixtures. Said that in the lecture notes on vocabulary, but it implies that two substances have mixed to form one new substance that is the same all the way through. The relationship: the solute is a substance that was dissolved, usually the smaller quantity, and the solvent is the substance that does the dissolving, usually the greater quantity. More solvent than solute. That's how it goes. So you're going to have to write small on this, okay? Sorry, not sorry. Or better yet, paraphrase what you're going to write in here. Don't write every word for word, paraphrase. Dissolving is always the first step. Dissolving, dissociation, and like dissolves like. Okay, dissolving is always the first step. Molecules break apart from one another and take on the form of the solvent. So the sugar molecules would split apart from the big crystal and go into the water and move around on their own. All soluble solutes do this. However, ionic compounds do something else. It's a second step, dissociate. Ionic compounds break down further. So the molecule compounds come apart, and then that falls apart into its positive and negative ions. Ionic compounds do this, not covalent compounds. Okay. Now the last little bit is that like dissolves like, is our way to remember how polarity works with solubility. Okay. In the scenario, we've got, oops, I got to fill this chart out here, so I'm going to go to the board. So polar things dissolve polar things. So if polar solvent is put into a polar solute, it will dissolve. If a polar solvent and a nonpolar solute get mixed together, it will not dissolve. Okay, so the two types of polarity have to match. Nonpolar and polar, no dissolving because they don't match. And then polar, nonpolar, and nonpolar will dissolve. Okay, so like dissolves like means that if their polarities are alike, then you will have them mix. If their polarities are different, they will not mix. And that's what this chart is supposed to tell us. Okay, so there's types of solutions. Alloys, solution or mixture of two or more metals, usually done to produce desired features like strength, durability, or reduced weight. Said that in the lecture on vocab. Here it is again. The other type of solution, aqueous. This is not going to settle upon standing. Aqueous solutions are water-based solvents, and water is referred to the universal solvent because it can dissolve ionics and covalents alike. If the solvent was alcohol, it wouldn't be aqueous solution, but it would be a liquid solution. Okay. Now there's some things that are not solutions as well. Colloids. These appear to be solutions, but fail the Tyndall test. The Tyndall test is when we shine a laser or a light beam through the solution. If we can see the beam of light in the laser in the solution, it is not a true solution. It is a colloid, a suspension, or an emulsion. A suspension is like two things are visible, sand and water or Italian dressing. You might shake it up and it looks homogeneous for a little while, but it doesn't stay that way. That's a suspension. An emulsion. Emulsion is a fine dispersion of minute droplets of one liquid in which another is not soluble or miscible. So this way we get oil and water to mix by making an emulsion. Oil and water don't have the same polarity. Oil is nonpolar, water is polar. So they shouldn't mix normally. But if you treat the oil and make an emulsion out of it, the two will mix. But it's not truly a solution. Only true solutions are aqueous solutions and alloys, I suppose. To test a solution, you do the Tyndall test. This is when we take a laser or a light beam and shine it through the liquid. And if we can see the light beam traveling through the liquid, we know there's microscopic particles in there bouncing the light off, which means it's not truly a solution. Only a true solution will show that the light doesn't appear to have a beam through the beaker. Ask me in class and I'll happily show you true and not true solutions using the Tyndall test. There's a reference table that helps us decide if something will dissolve or not dissolve, okay? And it's reference table F, okay? So an ionic compound that we're going to talk about here is NaCl. I'm going to write this on the board and I'm going to use the chart to show you if it's soluble or not. NaCl, the name of that compound is, of course, sodium chloride. And the way we figure out the solubility is we start with the second ion, the Cl. And we look at table F and we find where Cl is located. And I find it right there. It's a halide. Then you read to the column heading. It says that halides are soluble, but there's exceptions. And the exceptions apply to the first element in the compound. If that first element is Ag, Pb, or Hg, it would not be soluble, but it's not. In this case, NaCl is not an exception, so we would say this is soluble. It does dissolve in water. Next step, AgCl2. Well, this is silver chloride. And we're going to look at the chart and see how it goes. Well, I'm going to erase here and try again, okay? Silver chloride. Well, we start at the back end of the formula, chlorides. We're going to find that again. Chlorides are soluble unless the first element is Ag, Pb, or Hg. Well, look at that. The first element is Ag. So this would be insoluble. It would not dissolve in water very well at all. And then the last example we'll do here, AlPO4. This is aluminum phosphate. And to find its solubility, we'll start with the back end. We'll find PO4 on our table F, and then we'll decide if PO4s are soluble. So PO4, let's see, PO4, SO4, OH, S is PO4, phosphates. Well, phosphates are insoluble, means they don't dissolve in water unless the first element is from group 1 or NH4. Well, aluminum is from group 13, so it is not an exception to the rules, which makes this insoluble. Okay? Let's see what else we got here. Double replacement reactions, predicting solubility. This is pretty straightforward. We're going to swap our metal ions and make our new compound. So I'm going to get NaBr and MgCO3. Those are my two products. But then I have to apply my solubility rules. Okay, I'll go back for a second there. I'm going to apply my solubility rules looking at NaBr and MgCO3 using reference table F to decide which one is soluble and which one is insoluble. So NaBr, Br is a halide, halides are soluble, and NaBr is not an exception, so I would write AQ after this. CO3, carbonate. I'm going to look for carbonates on my table F. Carbonates are insoluble unless the first element's from group 1 or NH4. Well, Mg is from group 2, so that's not an exception. This is insoluble, so I put the parentheses S for solid afterwards. A couple more examples of double replacements and identifying precipitates. We are going to swap the positive ions to get our new compound. So I'm going to get CaCO3 and NH4Cl. But then I have to check those two products of the reaction on table F to see if one is a solid and one is aqueous or not. So CaCO3, carbonates, are insoluble unless the first element is from group 1 or NH4. Well, calcium's group 2, so this is insoluble. That would be a solid. And let's check ammonium chloride. Well, ammonium is on the list, and it says there's no exceptions ever. And chloride's on the list, and it says things are soluble. So we're going to go with aqueous in this particular example because it would dissolve in water. Last example, double replacement. We're going to swap the positive ions and probably run out of time here. So you're going to have to finish that one up yourself, I think. Don't you? My timer's done.